The cold cut deep near Lake Superior. Samuel Morrison learned that his first winter in 1846, when his fireplace consumed 3 cords of wood, yet left his cabin freezing. He had built his heating exactly the way every homesteader was taught. Stone fireplace, straight chimney, standard, and trusted. By spring, he had burned more wood than 2 men should need while precious heat escaped up the chimney. Across the northern frontier, settlers battled the same problem with heating built by the book and failing by the season. Samuel quietly dug an underground tunnel that captured smoke and stored heat in stone below his cabin floor. Neighbors mocked it as excessive, unnecessary work. But when hard winter returned, Samuel's cabin stayed warm 36 hours on one fire, while his neighbors' homes went cold nightly. What did he understand about heat storage that every other frontier builder missed? Samuel Morrison had arrived in the Michigan Territory with the same manual every homesteader carried, the Army Corps of Engineers Guide to Frontier Construction, printed in 1843 and distributed through land offices from Detroit to Duluth. The manual was clear on heating. Build your fireplace against the gable end, construct a straight chimney with proper draw, and trust the open flame to warm your living space. Every territorial agent, every lumber camp foreman, every established settler repeated the same advice. The method worked in Virginia, it worked in Ohio, and it would work on the northern frontier. Samuel had followed those instructions exactly. His fireplace measured 4 feet wide with a throat opening of 14 inches, built from local fieldstone mortared with clay and sand. The chimney rose 18 feet above his cabin roof with a cap to prevent downdrafts. He had split and stacked 8 cords of dry maple and birch before the first snow, more than the manual recommended for a cabin his size. Everything was regulation, everything was proven. But regulation had not accounted for the peculiar cold that settled over the Great Lakes country. When December winds swept across 200 miles of open water and struck his cabin walls, the interior temperature dropped 20 degrees in an hour. Samuel would stoke his fire until flames leapt 2 feet high, yet the heat rushed up the chimney and vanished into the night sky. He learned to wake every 2 hours to feed fresh logs into the firebox, but even then, ice formed in his water bucket 6 feet from the hearth. The problem was not unique to Samuel's construction. His nearest neighbor, Thomas Henley, had built his cabin using the same manual and suffered the same failures. Henley's wife complained that their children slept 3 to a bed under buffalo robes while the adults took turns maintaining the fire through the night. Down the ridge, the Kowalski family had given up on their fireplace entirely and moved their sleeping quarters into the root cellar where the earth provided more consistent warmth than their regulation heating system. Samuel had served 2 years with the Corps of Engineers before claiming his homestead, and military training had taught him to question systems that failed under field conditions. When standard procedures produced predictable failure, experienced soldiers looked for alternatives. By February, Samuel was studying the problem with an engineer's eye rather than a homesteader's desperation. The waste was obvious once he measured it. Using a mercury thermometer borrowed from the territorial surveyor, Samuel recorded the temperature of smoke as it exited his chimney. 160 degrees on a cold night when outside air measured 12 degrees below zero. Simple arithmetic told the story. Every cubic foot of that superheated smoke carried enough thermal energy to warm his cabin, yet the conventional system dumped it into the atmosphere. The Army manual had designed a heating system that functioned as a heat disposal system. Samuel's thinking had been shaped by more than military engineering. His grandfather had immigrated from Bavaria, where winters were equally harsh, but heating methods had evolved over centuries of scarcity. Bavarian farmhouses used masonry stoves that burned wood in a firebox, but channeled smoke through interior walls before venting outside. The principle was thermal mass. Stone and brick absorbed heat from combustion gases and radiated that warmth slowly over many hours. More importantly, Samuel had spent his first year in Michigan Territory working alongside Ojibwe guides who showed him how their ancestors had heated winter shelters. Their earth lodges and bark houses incorporated principles that no Army manual mentioned, using the ground itself as thermal storage, designing structures that held heat rather than allowing it to escape, and building fires that served multiple functions beyond immediate flame. These influences converged in Samuel's mind during a particularly brutal cold snap in March, when his regulation fireplace consumed half a cord of wood in 3 days, yet failed to prevent his remaining potatoes from freezing solid. If Bavarian masons could capture heat in stone walls, and if Ojibwe builders could use earth as thermal storage, then perhaps the solution was not to generate more heat, but to waste less of what he already produced. The idea that emerged was radical by frontier standards, but logical by engineering principles. Instead of allowing hot smoke to escape directly through a chimney, Samuel would force those combustion gases to travel through a system that captured their thermal energy. He would dig a tunnel beneath his cabin floor, line it with stones, and channel the smoke from his firebox through this underground passage before venting it outside. The heated stones would store thermal energy and radiate warmth upward through the floorboards long after the fire had died. When Samuel explained his plan to Thomas Henley, his neighbor's response was immediate and dismissive. "You want to dig a tunnel under your house? That's the most foolish waste of labor I ever heard. The Army manual works fine if you just burn enough wood." Henley's wife was more direct. "Sounds like you're trying to turn your cabin into an Indian lodge. We came here to build civilized homes, not live like savages." The criticism reflected a deeper tension between established method and frontier adaptation. The Army Corps of Engineers had codified building practices that worked in settled regions with abundant fuel supplies and moderate climates. Those same practices, when transplanted to the resource-limited extreme weather conditions of the northern frontier, produced consistent failure. But admitting failure meant admitting that official guidance was inadequate, and most homesteaders preferred to blame their own execution rather than question the system itself. Samuel understood this resistance, but had moved beyond caring about neighborly approval. His engineering background had taught him that successful systems were measured by results, not by conformity to established practice. If his underground heating system could reduce wood consumption while increasing thermal comfort, then the method was sound regardless of how unconventional it appeared to others. The social cost of innovation, Samuel realized, was often higher than the technical cost. Building an underground smoke tunnel would require perhaps 30 hours of digging and stonework, and during the skepticism and mockery of his neighbors might prove far more challenging than the physical labor itself. Samuel began construction on the 15th of April when the ground had thawed enough for digging, but before spring, planting demanded his attention. The tunnel route ran 20 feet from his fireplace foundation to a point beyond the cabin's north wall, following a precise 3-degree downward slope that would ensure proper smoke flow without allowing backdraft. This gradient was critical, too steep and the hot gases would rush through without transferring heat to the stones, too shallow and smoke would pool in reverse direction during windy conditions. The excavation required removing 18 cubic yards of clay and sandy soil, work that Samuel completed in sections to prevent cave-ins. He dug the tunnel 18 inches wide and 20 inches deep, dimensions calculated to provide sufficient volume for smoke passage while maintaining structural integrity under the weight of overlying earth. Each morning, he would excavate a 4-foot section, line it temporarily with split logs, then move to the next segment. The systematic approach prevented the tunnel walls from collapsing and allowed him to maintain the precise slope throughout the entire length. Stone selection proved as important as excavation technique. Samuel had learned from Ojibwe builders that certain rocks held and released heat more effectively than others. Granite and basalt from the lakeshore possessed high thermal mass but cracked when heated too rapidly. Sandstone heated evenly but crumbled after repeated heating cycles. The optimal choice was fieldstone limestone, abundant in local fence rows, which heated gradually and retained thermal energy for extended periods without structural failure. Samuel arranged the limestone in a specific pattern learned from his grandfather's descriptions of Bavarian construction. Instead of simply filling the tunnel with loose stones, he created a structured heat exchange system. The bottom third of the tunnel held fist-sized stones packed tightly to form a stable foundation. The middle section contained larger stones, each weighing 15 to 20 pounds, positioned to create air gaps that allowed smoke to circulate around their surfaces. The top layer consisted of flat stones that formed a crude arch, supporting the tunnel roof while maximizing surface area exposed to passing smoke. The critical innovation was the baffle system Samuel designed at 3 points along the tunnel. Using flat stones positioned at 45-degree angles, he created obstacles that forced the smoke to change direction and slow its passage. These baffles prevented the hot gases from racing through the tunnel without transferring their heat to the surrounding stones. The design borrowed from principles Samuel had observed in beaver dams, where strategically placed obstructions controlled water flow and created pools of different depths and temperatures. Construction of the tunnel exit required particular attention to draft management. Samuel built a vertical chimney shaft at the tunnel's end, rising 4 feet above ground level, but only 2 feet above his cabin roof. This height differential created enough draw to pull smoke through the underground passage, but not so much that the gases moved too quickly to deposit their heat. A simple stone cap with 4-inch openings on opposite sides allowed smoke to escape while preventing rain from entering the system. Samuel's first test came on a cold morning in early May when overnight temperatures dropped to 28 degrees. He built a modest fire in his fireplace using 2 armloads of split oak and observed the smoke's journey through his underground system. The initial flow was sluggish, requiring him to open the cabin door briefly to establish proper draft. Once the system began drawing correctly, smoke moved steadily through the tunnel, emerging as a thin stream from the external chimney rather than the thick column that had previously poured from his fireplace. Temperature measurements revealed the system's effectiveness immediately. Using his mercury thermometer, Samuel recorded readings at multiple points along the tunnel during the test burn. At the tunnel entrance, smoke measured 140 degrees. Midway through the passage, the temperature had dropped to 90 degrees as thermal energy transferred to the surrounding stones. At the exit point, smoke registered only 60 degrees, proving that the limestone had absorbed most of the combustion heat. More significantly, the heated stones continued radiating warmth long after the fire died. Samuel measured floor temperatures above the tunnel at hourly intervals throughout the night and following day. 6 hours after the fire extinguished, the floorboards directly above the tunnel registered 72 degrees, while areas away from the tunnel measured 58 degrees. 12 hours post-fire, the tunnel zone maintained 68 degrees. Even 18 hours later, when outside temperature dropped to 35 degrees, the floor above the heated stones remained at 62 degrees. The thermal performance exceeded Samuel's calculations. His engineering estimates had predicted the system would extend heating duration by perhaps 8 to 10 hours. Instead, the limestone thermal mass provided measurable warmth for a full day and night, fundamentally changing the heating requirements for his cabin. Rather than stoking fires every 2 hours through the night, Samuel could build one substantial fire each evening and wake to comfortable temperatures the next morning. Wood consumption dropped dramatically once Samuel refined his firing technique. Previously, maintaining overnight warmth required burning 6 to 8 pieces of split hardwood every 2 hours, consuming roughly 1 cord per month during winter. With the underground system, Samuel discovered that a single evening fire using 12 pieces of wood provided equivalent heating through the following day. Monthly wood consumption fell to less than half a cord, representing savings of nearly 4 cords over a typical heating season. The system demanded specific maintenance procedures that Samuel developed through trial and observation. Every 2 weeks, he removed ash buildup from the tunnel baffles using a long-handled wooden scraper fashioned from a broken axe handle. Monthly cleaning involved removing loose debris from the tunnel floor and checking the external chimney cap for blockages. Annual maintenance required removing and repositioning stones that had shifted due to thermal expansion, a process that took half a day but ensured continued efficiency. Samuel's success attracted attention from unexpected quarters. Joseph Kingbird, an Ojibwe elder who occasionally traded at the territorial post, examined the tunnel construction during a visit in late spring. Kingbird nodded approvingly at the stone arrangement and explained that Samuel had unknowingly recreated heating principles that Anishinaabe builders had used for generations in earth lodges. The technique of using underground thermal mass was ancient knowledge, Kingbird explained, though Samuel's application to a log cabin represented a novel adaptation of traditional wisdom to frontier conditions. Samuel discovered the limitations of his underground heating system during the brutal cold snap of January 1847, when temperatures plunged to 30 below zero for 6 consecutive nights. Despite the tunnel's efficient heat storage, cold penetrated through his cabin walls with such intensity that frost accumulated on the interior logs and his water bucket froze solid despite sitting directly above the heated tunnel. The thermal mass provided excellent heat retention, but the cabin envelope itself was hemorrhaging precious warmth faster than any heating system could replace it. The problem became quantifiable when Samuel used his mercury thermometer to measure temperature variations throughout the cabin during peak cold conditions. While the floor above the tunnel maintained 65 degrees, the temperature dropped steadily with distance from the heated zone. At shoulder height near the exterior walls, the thermometer registered 42 degrees. Near the ceiling, where heated air should naturally rise, temperatures fell to 38 degrees. The cabin's interior climate varied by nearly 30 degrees despite the underground system's steady heat output. Samuel recognized that heat loss occurred through multiple pathways simultaneously. Convective currents carried warm air upward toward the roof, where it escaped through gaps between the logs and around the chimney penetration. Conductive heat transfer moved thermal energy directly through the log walls to the frigid exterior air. Radiant heat loss occurred when the warm interior surfaces transferred energy to the cold walls and ceiling. His heating system was fighting a battle on three fronts, and thermal mass alone could not address the structural heat losses. The solution required understanding principles that frontier construction manuals ignored entirely. Samuel's conversations with Joseph Kingbird had introduced concepts of thermal barriers and dead air spaces that Anishinaabe builders had perfected over generations. Earth lodge construction used multiple layers of different materials to create insulating barriers that trapped air and prevented heat transfer. Kingbird explained that still air was nature's most effective insulator, but only when confined in small pockets that prevented convective circulation. Samuel began experimenting with insulation materials available on his homestead. Prairie grass, cut in late autumn when stems were dry and hollow, provided excellent air trapping capability when bundled tightly between wooden frames. Cattail fluff, harvested from the marshy areas near the lake, contained thousands of tiny air pockets that resisted heat transfer when packed into fabric casings. Bear fur obtained through trade with local hunters offered superior insulating properties due to its dense undercoat structure that trapped body heat in living animals. The most effective material proved to be a mixture Samuel developed through systematic testing. He combined chopped straw with clay slip and deer hair obtained from a tanning operation at the territorial post. When mixed in proper proportions, 1 part clay to 3 parts straw to 1 part hair, the combination dried into a lightweight fibrous material that could be packed into wall cavities. The clay provided structural integrity and moisture resistance, the straw created air pockets, and the animal hair added flexibility that prevented cracking as the material expanded and contracted with temperature changes. Application of insulation required modifying the cabin's interior construction without compromising structural integrity. Samuel built a secondary wall system using vertical strips of split cedar attached to the interior surface of his log walls. These furring strips created a 3-inch cavity that he filled with his straw-clay hair mixture, working from bottom to top in 4-foot sections. Horizontal boards salvaged from shipping crates provided the interior finish surface, creating an enclosed insulation system that prevented air circulation while allowing the mixture to remain dry. Ceiling insulation presented greater technical challenges due to the need to support the insulating material against gravity while maintaining access to the roof structure. Samuel solved this by installing a suspended ceiling system using lightweight poles tied with rawhide to create a grid pattern 18 inches below his roof beams. Over this framework, he spread canvas salvaged from military surplus tents, forming a shallow basin that he filled with loose cattail fluff to a depth of 8 inches. The suspended system reduced ceiling height, but created an insulating airspace that dramatically reduced heat loss through the roof. The floor required a different approach since Samuel could not disturb his existing tunnel system. He constructed a raised floor using split logs as joists, creating a 6-inch airspace above the original cabin floor. This cavity he filled with a mixture of dried leaves, grass, and wood chips obtained from his lumber preparation activities. Pine boughs layered between the organic materials prevented settling while adding their natural oils that repelled insects and rodents. Samuel's first comprehensive test of the insulated cabin occurred during a February blizzard that brought temperatures of 22 below zero with sustained winds of 30 miles per hour. The difference was immediately apparent. Interior temperatures throughout the cabin remained within 8 degrees of each other, ranging from 68 degrees near the tunnel to 60 degrees at the far corners. More importantly, these temperatures remained stable throughout the night without additional firing, something impossible before insulation installation. Fuel consumption measurements revealed the insulation's economic impact. During the coldest month of winter, Samuel's wood use dropped from the half cord required by his tunnel system alone to less than one-third cord with the addition of comprehensive insulation. The thermal barrier effect meant that heat generated by his underground system remained inside the living space rather than escaping through the building envelope. Each British thermal unit produced by burning wood now provided heating for extended periods, rather than quickly dissipating to the exterior. The insulation system required specific maintenance procedures to preserve effectiveness over time. Samuel discovered that moisture infiltration was the greatest threat to insulating performance. He developed a routine of checking interior wall surfaces monthly during heating season for signs of condensation that could dampen the straw-clay mixture. Annual maintenance included removing and replacing any insulating material that showed signs of mold or pest infiltration, typically less than 10% of the total installation. Construction of the insulated cabin attracted attention from Swedish immigrants who had recently settled 15 miles east near the lumber camp. Lars Anderson, who had built traditional Swedish log homes with thick walls and small windows, recognized Samuel's techniques as adaptations of Scandinavian building practices his grandfather had used in northern Sweden. Anderson explained that Swedish builders had learned over centuries that insulation was more important than wall thickness in extreme cold climates. The Swedish connection provided Samuel access to additional traditional knowledge about moisture management and air sealing techniques. Anderson showed him how to use pine resin mixed with oakum to seal gaps around windows and doors, creating airtight barriers that prevented heated air from escaping while keeping cold drafts from entering. This final refinement reduced Samuel's heating requirements by an additional 15%, bringing his total wood consumption to less than 1/4 of what neighbors used in uninsulated cabins with conventional heating systems. Samuel's first spring with his completed heating and insulation systems revealed a problem he had not anticipated during winter construction. Snowmelt from his cabin roof created a continuous flow of water that pooled against the foundation logs and soaked into the ground directly above his underground tunnel. As temperatures fluctuated between freezing and thawing throughout March and April, this saturated soil expanded and contracted in cycles that gradually shifted the carefully positioned limestone in his tunnel system. The foundation moisture problem became critical when Samuel noticed that sections of his floor above the tunnel no longer maintained consistent temperatures. Areas that had previously registered 65 degrees during cold nights now measured only 58 degrees, indicating that thermal transfer from the heated stones had diminished. Investigation revealed that groundwater had infiltrated the tunnel through gaps between shifted stones, creating pockets of mud that insulated rather than conducted heat from the limestone to the cabin floor. Samuel recognized that water management required the same systematic approach he had applied to heat retention and insulation. Successful frontier construction demanded understanding how different natural forces interacted with building systems over seasonal cycles. His underground tunnel functioned perfectly as a thermal system, but had created vulnerabilities in foundation drainage that conventional cabin construction avoided by keeping heating systems entirely above ground. The solution came from observing how water moved across his homestead during different weather conditions. Samuel spent 2 weeks in early spring tracking drainage patterns, noting where snowmelt collected, where ground remained saturated longest, and where natural slopes directed surface water. He discovered that his cabin sat at the convergence point of 3 minor drainage channels that carried runoff from higher ground during spring thaws and heavy summer storms. French drainage techniques, learned from conversations with territorial surveyors who had worked in Louisiana, provided the foundation for Samuel's water management system. The principle involved creating underground channels that intercepted groundwater before it could reach building foundations, directing it away through gravel-filled trenches that maintained flow even when surrounding soil became saturated. Samuel began by digging a drainage trench around the uphill perimeter of his cabin, following the natural contours that directed water toward his foundation. The trench measured 18 inches deep and 12 inches wide, following a consistent 2-degree slope that ensured water would flow toward a collection point 50 feet from the cabin. This gradient was crucial. Insufficient slope allowed water to pool in the trench, while excessive slope caused erosion that would eventually undermine the drainage system. The trench required specific layering to function effectively throughout seasonal changes. Samuel placed large field stones, each weighing 10 to 15 pounds, along the bottom to create a stable foundation that would not shift during freeze-thaw cycles. Over these foundation stones, he laid a 6-inch layer of gravel ranging from pea-sized to walnut-sized pieces, sorted to ensure proper water flow without allowing fine particles to clog the drainage channels. The critical innovation was Samuel's use of split cedar logs to create a covered drainage system that prevented surface debris from entering the gravel channels while maintaining access for maintenance. He positioned half logs over the gravel layer with the flat side down, creating arched spaces that allowed water to flow freely while supporting the weight of overlying soil. This technique borrowed from beaver dam construction principles Joseph Kingbird had described, where overlapping materials created strong structures that channeled water flow without impeding it. Roof water management required a complementary system that intercepted precipitation before it reached the ground around the cabin foundation. Samuel constructed gutters using split logs hollowed with an adze, mounting them along the cabin's eave line with wooden brackets cut from oak branches. These gutters collected rainwater and snowmelt from the entire roof surface and directed it through wooden downspouts to collection points that connected with his underground drainage network. The downspout design incorporated splash blocks carved from sandstone that dissipated water energy and prevented erosion at discharge points. Each splash block measured 2 feet long and 8 inches wide, with a shallow depression that spread concentrated water flow over a broader area. Samuel positioned these blocks to direct roof runoff into swales he had dug that carried water away from the cabin foundation, following natural drainage patterns. Samuel's drainage system required integration with the existing landscape to function during extreme weather events. He created earth berms using soil excavated from his drainage trenches, positioning these raised areas to direct surface water away from vulnerable areas around his cabin. The berms followed contour lines that worked with natural topography rather than fighting against established drainage patterns. The most sophisticated element was Samuel's construction of a retention basin 60 feet from his cabin where all drainage channels converged. This basin, measuring 8 feet across and 3 feet deep at its center, collected water from both his roof gutters and foundation drains during heavy rainfall or rapid snowmelt. Overflow from the basin directed water toward a natural creek that carried it safely away from his homestead without causing erosion. Testing of the drainage system came during the spring flooding of 1848, when a week of warm weather melted accumulated snow, while simultaneous rainfall added additional water volume. Samuel's gutters and drains handled the combined water load without allowing any moisture to accumulate against his cabin foundation. Temperature measurements above his tunnel system remained consistent throughout the flood period, confirming that the drainage improvements had preserved the thermal performance of his underground heating system. The economic benefits of proper drainage extended beyond protecting Samuel's existing investments in heating and insulation. Dry soil around his cabin foundation prevented frost heaving that had damaged neighboring cabins, saving him the cost of releveling floors and repairing foundation logs that shifted during freeze-thaw cycles. The controlled water management also created opportunities for Samuel to establish a kitchen garden in areas where controlled irrigation from his retention system provided reliable moisture during dry periods. Samuel's drainage techniques attracted attention from the territorial road supervisor, who recognized applications for managing water flow around bridges and culverts that frequently washed out during spring floods. The supervisor hired Samuel to construct similar drainage systems at 3 critical road crossings, providing additional income that helped offset the labor invested in developing his water management techniques. The integration of heating, insulation, and drainage systems created a cabin environment that functioned effectively throughout seasonal extremes while requiring minimal maintenance and fuel inputs. Samuel had developed a comprehensive approach to frontier construction that addressed multiple environmental challenges through coordinated technical solutions, each reinforcing the effectiveness of the others while drawing on traditional knowledge adapted to local conditions. The winter of 1849 brought the most severe weather in territorial memory when a massive Arctic storm system stalled over the Great Lakes region for 12 consecutive days in February. Temperatures dropped to 41 degrees below zero, and sustained winds of 45 miles per hour created conditions that territorial officials later documented as unprecedented in frontier records. The storm provided the ultimate test of Samuel's integrated building systems against the most extreme environmental stress the northern climate could deliver. Samuel had prepared for severe weather by developing systematic procedures for storm operations that went beyond simply maintaining his heating system. He established protocols for monitoring system performance during extreme conditions, using techniques that allowed him to identify potential failures before they became critical. These procedures included hourly temperature readings at 16 specific locations throughout his cabin, daily inspection of drainage outflows for ice blockages, and careful tracking of wood consumption rates to detect any decline in system efficiency. The monitoring approach required Samuel to create measurement tools that provided accurate data under harsh conditions. He fashioned temperature recording stations using mercury thermometers mounted in wooden frames at precise locations. Floor level above the tunnel, shoulder height near exterior walls, ceiling level at cabin center, and exterior readings taken through a small observation port he had installed in his north wall. Each station was marked with carved notches that allowed consistent positioning of thermometers even in darkness or blizzard conditions. Samuel's fuel management strategy during the extended storm demonstrated the importance of system redundancy in extreme survival situations. Rather than relying solely on his efficient underground system, he prepared auxiliary heating capability using a small metal brazier positioned to heat his sleeping area directly if the main system failed. He stockpiled split kindling in graduated sizes, from pencil-thin starter wood to wrist-thick sustaining fuel, organizing these materials in a sequence that allowed rapid fire building without waste or delay. The storm's intensity revealed performance characteristics of Samuel's systems that had not been apparent during normal winter conditions. Wind-driven snow accumulated against his cabin walls to depths of 6 feet, creating insulation that actually improved his building's thermal performance by adding an exterior barrier that reduced heat loss through the log walls. The drainage system prevented this snow accumulation from creating ice dams that could force meltwater into his foundation when temperatures eventually moderated. Samuel's neighbor Thomas Henley faced catastrophic system failures during the 4th day of the storm when his conventional fireplace could not generate sufficient heat to prevent interior freeze-up despite burning wood continuously. Henley's cabin interior temperature dropped to 18 degrees above zero, causing his water supplies to freeze solid and forcing his family to abandon their cabin for the relative warmth of their livestock barn. The Henley family's survival depended on body heat shared with their cattle and horses, a desperate measure that frontier families adopted only when their heating systems failed completely. The contrast became measurable when Samuel began recording comparative data between his cabin's performance and conditions in neighboring homesteads. During the storm's peak intensity, Samuel's interior temperatures ranged from 64 degrees near his tunnel system to 58 degrees at the cabin's extremities. Henley's cabin, measured through visits Samuel made to check on his neighbor's welfare, registered temperatures between 22 and 34 degrees, despite continuous firing of his conventional fireplace. Samuel's wood consumption during the 12-day storm totaled less than 1 1/2 cords, burned in controlled evening fires that provided heating for complete 24-hour cycles. Henley consumed 4 1/4 cords during the same period while achieving inferior results, demonstrating that Samuel's integrated systems provided nearly 3 times the heating efficiency of conventional frontier construction. These measurements, recorded in Samuel's daily log, provided quantitative proof of his method's superiority under extreme conditions. The storm's conclusion brought requests for technical assistance from homesteaders throughout the region who had witnessed the dramatic performance differences between Samuel's systems and conventional construction. 7 families approached Samuel during March 1849, seeking instruction in underground tunnel construction, insulation techniques, and drainage management. Samuel recognized that knowledge transfer required systematic teaching methods rather than casual explanation of techniques. Samuel developed a structured apprenticeship program that allowed other homesteaders to learn his methods through hands-on construction projects. Rather than attempting to explain complex thermal and structural principles through verbal instruction alone, Samuel required students to participate in actual building work where they could observe cause and effect relationships directly. Each apprentice committed to working on Samuel's homestead for 2 weeks in exchange for instruction in specific techniques they could apply to their own construction projects. The teaching process revealed aspects of Samuel's methods that he had developed intuitively but had never articulated systematically. When forced to explain his decision-making process to apprentices, Samuel recognized that his techniques followed consistent principles that could be applied to various frontier construction challenges. These principles included working with natural forces rather than against them, using multiple reinforcing systems rather than depending on single solutions, and adapting traditional knowledge to local conditions through systematic experimentation. Documentation of Samuel's techniques began when territorial surveyor James Crawford recognized their potential applications to government construction projects. Crawford arranged for detailed drawings and written specifications to be prepared by the Territorial Engineer's Office, creating the first technical manual that described underground thermal mass heating adapted to North American frontier conditions. These documents were distributed to army posts and territorial offices throughout the northern frontier regions. Samuel's innovations influenced construction practices far beyond his immediate region when territorial officials incorporated his drainage and heating techniques into standard specifications for government buildings. Military posts constructed after 1850 routinely included modified versions of Samuel's underground heating systems, and territorial courthouses and land offices adopted his insulation methods for improved fuel efficiency and occupant comfort. The legacy of Samuel's integrated building approach extended into the 20th century through homesteaders who carried his techniques westward during later territorial expansion. Norwegian and Swedish immigrants who learned Samuel's methods in Michigan applied them to construction in Minnesota, Dakota Territory, and eventually Alaska, where extreme climate conditions made efficient heating systems essential for survival. Modern off-grid construction continues to rediscover principles that Samuel developed during his frontier experiments with thermal mass, passive solar design, and integrated building systems. Contemporary builders working in remote locations face identical challenges of fuel scarcity, extreme weather, and limited resources that Samuel addressed through systematic application of traditional knowledge adapted to specific environmental conditions.